Good evening, everyone. My name is Dr. Vahram Martirosyan. I am currently teaching at the Higher Colleges of Technology in Abu Dhabi. So my focus is computer science and mathematics, and my career has been also in computer science and a little bit in mathematics for a long time. And C++ was one of my first languages that I have studied and that I have used at just for work. In particular, I've been doing high performance computing. I have been dealing with operating systems, modules, have been creating actually a compiler using C++. So it was a very interesting journey. And during this time, I have been gathering knowledge and experience. So when I started, it was back in 2000, year of 2000, and C++ was very simple in those days. Now, as you probably know, we are getting new versions like in 3 years, and it has grown too much. And yeah, you have seen a lots of memes, I believe, about how complicated it is nowadays. And yeah, it is. But our focus is not the complicated new features that are very disconnected from the reality. We're going today to focus on more practical things which are there, like they are useful for everyday programming. So we're going to talk a little bit about pointers, about some memory related topics, arrays, functions, and we are going to do some error handling. We are going to face errors and overcome them. But it's not all. So I'm planning also to do some test-driven development demo, which is kind of a strange, practical, methodology, which helps really to improve the code quality. Okay, so let's do a deep dive. I'm going to use my environment. So my environment is Visual Studio Code, and it is connected to a WSL server on my machine, Ubuntu. So my environment is actually Ubuntu, but the editor is Visual Studio Code. You can do, like, if you want to go in parallel with me, it's okay. So you can have your own environment. It doesn't matter much. Just we need a compiler, and yeah, we need make to build the system. It's very usual to have. I believe you all have it. And one small thing, we are going to use Google Test. So if you want to be in sync, you can have the Google Test framework installed. We are going to use it a little bit later. So here we have a make file. I have created it just to not waste our time. It defines all the main targets that we are going to build, and also it has the clean target to remove everything created. And I'm just going to do make this, make that to have a fast build process. So what we're going to do is actually we're going to write a program that can factorize a given number. So we're talking about prime factorization, of course, and that problem itself is very interesting and tricky because you cannot easily factorize large numbers, and that is what we have in the foundation of encryption, modern encryption. Yeah, but we're not going to solve that kind of problem, okay? We are focusing on small and daily issues that every program is going to face while starting or even doing C++ for several years. So it is very usual to face those problems that we are going to face today. So here is my kind of main CPP file. It is going to be used for the interaction with the outer world. So IO stream is necessary for that. We are going to ask the user to enter a number, right? Like enter a number, to factorize, factor. So then we are going to declare the number itself, and read the input. Everything is clear, I believe. So I hope that my audience, well, has the C++ knowledge. So I'm not going to get deep into every detail, but anyway, if you have any questions, just let me know. No problem. So after getting the number, we are going to factorize it somehow. Now we are going to assume that somewhere there, out there, we have a function that will do that factorization. So I'm just going to call it like get vectors. I will give that number that we just got, and I will expect that it will return a pointer to an integer, which we will name vectors. So vectors equals get vectors over numbers. Okay. And then we just need to print, right, somehow. So the factors of this number are, and then with the for loop, we are going to kind of print them. But here is the contract. So we need to have a contract between the caller and the callee. So it is a very usual practice in programming when we have two sides, the caller, this main function, right, and the callee, the get vectors. So the contract is usually defined by the callee, okay? The function itself, get vectors, is supposed to create that array of vectors and return a pointer to it. But as you probably know, in C++, we don't have a proper way to know how long an array is. So we have a pointer which points to the beginning of the array, but how long is that array? So we don't know that, and in order to, oh, maybe I will make it a little bit larger, I guess. I hope, yeah. So in order to understand where the data ends, we need to have that contract. So in our case, we're going to say that, well, vectors are prime numbers, right? So they are greater than equal, greater or equal than 2, which means we are not going to have zeros or negative numbers there. So we can decide that 0 is the end, okay? So if we meet a 0 value in the array, then this is the end, okay? So actually we can check if the vectors I is, oh, I is, no, not I. If vectors I is not 0. So this condition means that we are still going over prime numbers. Well, right now we have a confusion probably because we have a pointer and we have, well, looks like an array access. Actually, in C++, pointers and arrays are kind of the same thing. So the name of the array is actually a pointer to the first element. And if you do pointer arithmetics on that pointer, you can access the next elements, given that you have the proper data type, right, the element type. So now we know this is an integer and everything is quite smooth. So we will go through that array using this pointer. It's okay. I mean, from the compiler's perspective, everything is fine. And we are looking for the 0 value. As soon as we don't get any zeros, these are the prime factors. So we need to print. Okay, and at the end, I will just put a separator because I don't want to have that just the printing convenience. I want to have a beautiful user-friendly output. So as you can see, we have this red line under the get vectors. It is undefined. Well, of course it is, because we didn't give any hint, right, to the compiler. So in C++ and in C even, there is this tradition of creating header files. So we are going to do that. Now, this is the factors.hpp. In a header file in C++, we put the prototype or the declaration of the function. So it is called get vectors. And we just name its argument types. We can even omit the names. I mean, it's optional, but we can put it. It doesn't matter, absolutely. What matters is that in the main file, we need to include this, okay? So we include this factors HPP, and now the compiler is happy. I mean, the compiler now knows why, because we have included the file. So the compiler has the prototype. The prototype just tells that, yes, there is a function, get vectors. It, yes, really accepts an integer and returns an integer pointer. So the compiler can just go on. I mean, from the compiler's perspective, the code can be translated into lower languages. Like in our case, we are going to use CLang. So the languages are LLVMIR, and then it can be transformed, optimized, and then it will be translated to some assembly language. Well, in our case, it is going to be x86, 64-bit assembly language. Then it will be translated, converted into an object file. Okay, in that process, the compiler doesn't even need to know where is this function. Well, actually, it doesn't exist. So we can check it running CLang++. I'm not doing make right now because we don't have that target. So CLang++, I will compile main.cpp with this option, so -c, which means just compile without actually getting the executable file, so without linking. And after the successful compilation, we see that main.o file is successfully created. Like, yeah, the compiler doesn't see any issues, but there is an issue. I mean, if we try to do make, we will see that the linker is complaining. Okay, so the function is not implemented. Sure, we have a missing piece of our puzzle. So that's why we have the CPP file, factor CPP, and here I'm going to define that function. So it returns a pointer. It is called get vectors. I will give the number, but I will not implement it so far because there's no need. Now, if I use make again, we get at least no errors. Okay, the compilation was successful, and we have this output. It is called factorizer. Why is it called like that? Because we have this make file, and here it is. So when we run just make, then we do make all, which depends on main, which means we run this. We run to this target, and this is the command which takes main CPP and factor CPP. So it is a two-file compilation, and it produces the factorizer executable file. That is the name. So hope everything is fine so far. Now we have the executable file, and we can call it. I mean, yeah, if we are just in a hurry, then we can start. So enter a number. Okay, let's take 10. What about 10? Oh, yeah, illegal instruction. So this is very, very common. I mean, when you start dealing with pointers, arrays, and starting like to do a multi-file project, okay, let's call it like that, a project that is not trivial, just not just doing a simple comparison of numbers or so something real, then you usually have this kind of issues popping in, like illegal instructions, segmentation of faults, double free, corrupted memory, etc., etc. So this is one of them, and this is just the first time we meet it. Let's dig a little bit deeper to understand what is this. Okay, illegal instruction. Why? What did we do illegal? Like, how could we even write anything illegal? Well, the point is, we had a warning, right? We kind of skipped it, but it is there, and it says that a non-void function does not return a value, which is in fact a problem. So whenever you have a warning, it means your code is not perfect, and it means that one day at some client's machine, client's environment, it is going to crash. So this is the case, and we are happy that we see it right here. We can fix it. So what is the problem? There is no return statement, and from the CPU's perspective, it means that when the CPU gets to the end of the function, from our understanding, that is the end of the function, right? But from the CPU's perspective, there is no end, because you don't have the return read statement. If we talk about x86, no read which means the CPU is not going to return to that location where you called it from, right? We called it here. So the CPU must get back and do the next instruction. Of course, this is the C++ code. I don't want to open the assembly file and check on that, but we can. So that is a topic for the next next sessions. But yes, we can do that. We are not just going to do it today. So what we can say it is the following. As there is no read instruction, then the CPU is just going to continue executing the next instructions in the memory, which is a huge security issue. And most probably the CPU is going to run on something that is not even an instruction. It can be data, or it can be just a garbage. Okay, let's use that word. So garbage means something that we don't know why it is there, we don't control it. And when the CPU gets to that kind of situation, then there is a security problem. That's why the compiler will just emit a code, seeing that the return statement is missing. The compiler will emit a code which will just instruct the CPU to stop the execution and tell the user, well, using the CPU exceptions, that, well, I don't understand what is written here. Okay, illegal instruction actually means that the CPU doesn't understand what is written there, but that is an instruction. Okay, the CPU reads the instruction which tells it to tell the user that it doesn't understand this instruction. Yeah, I know it sounds a little bit strange, but this is how the world is created. So in order to avoid illegal instructions, okay, let's say the Q is actually to do the return, okay, in order to avoid illegal instruction situations. So we just need to return something. Okay, let's return something. That something must be a pointer to an integer. As far as I don't know what to write, I can just return a null PTR, which is a spatial value, kind of, and it means zero pointer. So zero pointer is another big deal in the world of C++, because it is very usual to have zero or uninitialized pointers, and when we touch them, we are in trouble. But we don't know much about it, and we want to continue. Okay, now do we have that warning? Well, we don't. So, by the way, concerning the warnings, so usually we will not see all the warnings all the time. For that, we have a special compiler flag w all, which means that I want to see all the warnings. So if I do a make again, well, right now we don't have any warnings, but just for your consideration for future, keep in mind that if you miss this flag, then some warnings can be just omitted. You will not see the warnings, which means you will not be aware of some problem in your code. Okay, and one day you are going to face it as a client bug or something like that. So always keep that WAll and even more specific compiler flags like effective C++ or some, there are very special flags like for stack protection, etc. There are a bunch of warnings that you can enable. So enable all of them because they help you to keep your code safe, secure, okay, and high quality. I mean, just eliminating all the warnings, you get a higher quality code. Okay, where are we now? We can run it. Okay, let's run it. I will give 10 again, and now we have another issue. Now it is a segmentation fault. Well, expected, right? We were looking for that. Why segmentation fault? Why were we expecting it? Because I returned a null pointer, and on the next line, after returning it, well, a couple of lines after it, I try to access that pointer, okay, here. So accessing a null pointer is an undefined behavior according to the C++ standard. So null pointer, the reference leads to undefined behavior, which means you don't know what will happen. So undefined really means we don't know. And it also means that it depends on the compiler, on the environment, on the CPU, okay, on many things. So in particular, in this case, a null pointer is handled by the, okay, a null pointer dereferencing is handled by by the operating system, and the operating system doesn't actually map that 0 address to anything real. And when you try to access it, the CPU is raising an exception saying that I don't know where this pointer points to, okay? But in some setups, in some different environments, like on a microcontroller or in real mode of the x86 processor, you can actually access a null pointer. But still, it is an undefined behavior. It is just on your risk. You must check and verify everything before doing that, okay? But right now, of course, the operating system will not let us access. But another strange thing, if that happened on this line, then where is our output? We don't see the output, like it should say that factors of something. Where is this line? So we can think that what if the problem is here? Maybe get factors causes. You see, the segmentation fault doesn't actually tell us where that happened. We need a debugger, right? We need to understand a little bit of reading that GDB language or something to understand what is going on. But at least we see. Okay, line 11. Flush is a regular method of Austrian class. Actually, the cout object can give us access to flush. And if I rebuild and run, give the same input, we can see this part of output, which says factors of 10 are and segmentation fault. So it means this line was really being called. It was buffered in the output stream and never was flushed to the actual output device because the process would be killed, okay? When an exception is rising, so we are talking about CPU exceptions, okay? It's not the C++ exception. We are talking about CPU internal faults. So when a fault rises, operating system is going just to kill the process. And in that case, whatever is in the output buffer stays in the output buffer and never gets flushed. So if you want to make sure that whatever you type, print, okay, try to print, will be visible, you can do flush or you can use std_endl. But in our case, std_endl will bring the cursor to a new line, so we don't want it. That's why I will call flush. But it's very unusual. I mean, usually we don't have a situation like this. We are just in the process of troubleshooting segmentation faults. That's why we need this flush. But it will be gone soon. So now we know that there is a chance. I mean, well, there is always a chance that any function that returns a pointer can return a null value, right? So we must always check for null values. How we do that? Well, we can do like this, but I would suggest a couple of improvements here. So first of all, there is a good practice which comes from early days of C programming, where one would compare null with factors instead of comparing factors with null. So why would we do that? Because when in old days, the compiler would not give any warnings if you write instead of equals an assignment, okay? Which means the following: I write vectors, assignment, and then null PTR. Of course, nowadays everyone knows that it's an assignment, right? So the compiler will probably give a couple of warnings and notes and hints what to do, how to fix that. But other compilers would not. I mean, there are compilers that will not give you any warnings, like GCC without WAL. You will not get a warning about this situation. But if you put null PTR at the first position, okay, you write null PTR equals factors. It's a very small trick, but it can save your time. I mean, your time wasted on debugging. Just putting like this, it will never allow you. I mean, now the compiler knows on the left hand you have a value, on the right hand you have a variable, so you are doing it wrong. Okay. Now, this is just a recommendation. Of course, you can ignore it, but it saves a lot of time. Another thing is about the error messages. So pay attention that error messages should be printed using CERR, not cout, because these are error messages, right? And the error messages can be separated and redirected to another location, like you can log them or just throw them away if you don't need them, while you can keep the output and show it to the user. Okay, these are two separate streams and they can redirect it and manage separately. So using CERR for error messages and return non-zero value. So non-zero value from main means the program didn't succeed. Whatever it was doing, we don't know what was the purpose of the program, but whatever it was supposed to do, it failed. Okay, and there can be a documentation which will clearly say what is the purpose of 1 or purpose of 2, non-zero error codes. While here we have 0, which means everything was fine. And one more thing about CERR, it has no buffering. So whatever you print, it just gets immediately to the output device or file, okay, into the output. So this is the correct way of handling things. Now, if we compile and run, we will probably see a proper message saying that, well, it returned a null pointer. So we just don't see any segmentation faults and stuff like that. We are happy. And now a rule of thumb. So said, whenever you call a function, a non-void function, make sure that you have an if statement that properly checks the output or the error code or the status that the function returns. And usually you would better to have non-void functions. I mean, if you check the POSIX user's manual or programmer's manual, you'll see that all the POSIX functions are non-void. They all return some status code in order to show whether everything was fine, okay? So usually non-void functions must be checked. Usually you are going to write if just after you call the function. Of course, you can say that this is not even C++. This is C programming. Yes, sure, but C++ is so multimodal. You can have all the possible paradigms, programming paradigms in one language. And this is one of them. This is the procedural C++. You can call it C programming, but it is there. I mean, many people do that. And it is okay. So you are not supposed always to write object-oriented, meta programming, compile time, concepts, etc. No, sometimes you just need a simple program that will do a simple task, but you want to do it properly. Okay, using pointers, arrays, etc., and be safe. This is the way. Okay, now we have get factors. It doesn't do much. So let's start doing something. I will create some array. I'll call it result. I will make it, let's say, 100 characters long, numbers long, and I will return it. Sorry, result. So at least not to have that situation. Now, if I try to make, I will get a warning which says address of stack memory associated with local variable result is returned. Always pay attention to the warning. So this warning shows me a very fundamentally wrong situation that I just created in my code. Okay, what have I done? I created a local variable of size 100 elements, right? 400 bytes, which a local variable means it is going to automatically create it as soon as the function gets called in the stack, okay, in the stack frame of that function. And it will be destroyed as soon as the function returns. So I've created such a variable and have returned its name. Actually, it is an array, so its name is a pointer to the first element in that array, which means I'm returning an address to the stack frame, which is going to be destroyed right after I return it. And that's what we get. Okay, so don't do that. And usually, yeah, we are going to see really strange things. And this is an undefined behavior, okay? Whatever you get, you must be happy. You can get anything, like it can even crash the program. we have the warning, so we must not do that like this. Okay, this is not a proper solution. Never return an address of a local variable. Okay, as we are not going to create a proper program that follows all the best practices and architectural advices, we are just trying to go through this demo. I will move it to the global scope, but a big disclaimer, okay? Not the best solution. I mean, a very bad solution, not the best solution. So don't do that, okay? But works for demonstration purposes, literally, okay? So the correct way of doing things would be to create a class that would encapsulate the result, its length, whatever we need, and the caller will have to deal with that class interface, which would probably guarantee that everything will be smooth. But for the demonstration purposes, it is okay. We have the disclaimer, right? Now we're out of any warnings, and if I run it, we still are not there, okay? But actually, we don't see the garbage here. The garbage is gone because global variables are automatically initialized with zeros, filled with zeros. Why is it like that? Because global variables are stored in a spatial segment in the executable file sector, which is called BSS. And the idea of the BSS is to show how many bytes of zero initialized data we need. They don't consume space in the executable file, okay? It's just the length. So in this case, 100, that's all. It will just, I mean the number, not 100 bytes, okay? It will just contain a number, 100, which, sorry, 400, yes, we have 100 integers. So 400 telling the execution environment that we need 400 bytes filled with zeros, okay? Global variables make sure that the location, that area is filled with zeros. That's why we don't see anything, because our logic was to iterate over the factors up to some zero value. Well, the first one is zero, like it is all zero. Okay, setup is done, the function is ready. We have no warnings, like maybe we can start with the algorithm. So the algorithm looks like this. Well, I just need to check if some prime numbers are factors. Like if I divide my number to the prime number by the prime number, I will get a zero remainder, right? That is the idea. Well, for that, I need to iterate over the prime numbers, make the division, and check. So we will start with some prime number. Let's call it next prime number, because I'm going to iterate next prime. I will start with 2, okay? And then if number divided by with percent sign, which means that is the, I need a reminder, okay? By 2 equals 0, it means we have a candidate, like we have found a solution, right? One of them. So we need to add it to the result. Of course, we can write it like this, but this is not a proper way of doing things. So I will just transform it into another function. So now we are dealing with functions. The logic, the idea behind function is the following. Have a separated, isolated piece of code which can handle an operation quite isolated, okay, and perform one job. Better to focus on one thing. So get factors. I mean, if I start implementing that, adding factor code here, it will get longer and longer. So I want to keep it as short as possible to be able to consume it just by looking at it, okay? That is kind of a dream. So that's why we're going to have a new function which will not return actually anything, I believe. It will just add a factor to the existing array, but we're not going to use this bad choice. We're going to still stick to well, we already have that global scope, right? So just let's continue using it. And even no need for the 0 because it will be initialized by a 0 value. But anyway, so here I have this factor I need to put it into the result at some position. The position is being tracked globally again. And then I need to move the index forward. And there is one more thing. We are not done because we have a null terminated array. So I must put the 0 at the position where the index points. Okay. So calling at factor 2 will add 2 as a factor. I mean, yeah, of course, it's not a proper way to write the algorithm, but we are still constructing, just in the process of construction. So next prime, we start at 2. We check if number can be divided by next prime, then add next prime to the factor list and divide it by next prime. So hopefully we have something. Right now we are not absolutely empty-handed. We have something. So we can take, for example, 4, and it will be kind of factorized. We see that 2 is one of its factors, probably. Well, it is there at least, right? Or we can try another number. What about 6? Well, 2 is still there. Like, yeah, we have done a great job. Now we have a partial factorizer. Okay, but we actually need the next number, right? Where is that next prime number thing? So for that, we will use a loop. So we will go for some while. And yeah, probably while number is greater than 1, we are going to do the following. Let's see. So I'm kind of constructing the code, okay? If it gets divided, then let's add it to the factors, do the division, and then increment, or we need the next prime number, right? So what does that even mean? Well, we can call a function. So I will assign next prime the result of a function which is called get next prime. Let's call it like that. I will give a prime number and expect the next one. But now we need to start at 0 because here we have this call in the beginning of the loop, right? So as soon as the process starts, we will call it. We will get the next comparing to what? Well, to 0. So it will be the first one. And then we will continue. Now, this is another piece where we isolated a step, a piece of, well, a big step of our algorithm into a separate function because it makes sense, because it is really something isolated. So get next prime, let's see. Well, I believe this is not what we want. Here it is. So now, well, anyway, it can just return 2 so far, just to make sure that we didn't break anything. So when you follow, as you follow my writing code, you will see that I'm trying to compile and run the program as soon as I get a big change. Actually, I got a change. Now it gets compiled, and I try to compile and run periodically. So right now, I executed it, and as you can see, it hangs, which means I have an endless loop somewhere, right? It hangs, so I don't see any output. So I hit Control-C and go and check what happened. So what actually happened is the following. This next prime number is just 2, well, for some time. And so if we divide it by 2 once, and then it becomes 5, and then we start dividing by 5. So it's wrong, right? Something is wrong because we don't have all the other prime numbers. We need next prime number, really. We need that logic. So for that logic, let's create, well, let's implement it. So I will start at some point, which is going to be the next number after the current, okay? Next number after current, which is, okay, let's clean the code. I don't want to get stuck on the same number. That's why I moved to the next, just from the beginning. And I just try to check if it is prime, right? That the start. If it is prime, then that is what we need. Just return it. So looks like we have a missing piece of the code because we have if, but we don't have its else case, and we don't have a return statement after the for statement. But our guarantee or our hope is that there is always a bigger prime number. Like if we continue, we will find it. It's not an endless loop, okay? We will find it eventually and we will stop. And another separated piece, that is the check for is prime. So I'm going to create that bool is prime function. I will give the number. It will do its best to find whether it is prime. I hope there's no need to explain this code. But if there is, please let me know. So here we have this check. Well, there are no prime numbers less than 2 for sure. This loop is not very optimal one because we're not focusing on high performance computing here, just trying to go through the algorithm, make it run. Okay, looks like now we have all the pieces there. We can run, we can factorize things. Okay, well, what about 15? Still okay. What about maybe some prime number like 17? It is still okay. So looks like the code is ready, right? But don't get fooled. The code is not ready because if I try something like this, we are still not there, okay? 4, which is just a very small number, it could be easily factorized, causes our code to freeze, like to run forever. Why? Because in the reality, the same prime number can be a multi-factor, multiple times factor, which means when we check this and divide, we can still end up with a number which has the same prime number as a factor again. We miss that point. That's why we get into an endless loop, because we just move to the next one. But 4 cannot be divided by 3, by 4. Well, it can be divided by 4. It's not a prime number, sorry. By 3, by 5, by 7. So what we should do is actually do a if to while transformation. So instead of if, we just put while, which means we generalize. We say, do this same thing as long as the condition holds, not just once. Because we did it once, and 4 didn't get properly factorized. What about now? Well, 4 is there. What about 10? Is it still? Yeah, it is still being factorized. What about a larger number like 4096? This is a special number, right? It is a very unique and interesting number. Oh, it gets factorized. Looks like we have 12 tools there. So it is more or less fine. Now we have implemented a function which calls another function, which calls another function. So we have a chain of functions. Each of them does a simple, like very, very simple sometimes operation. But what is important, we have a good visibility of what is going on. I mean, if I take all these lines of code and put them inside this poor function, it is going to become 50 lines long. And it will not even fit into the screen. So there are different approaches to this. Someone would say that a function should fit into a screen, like a 25 by 80 characters terminal. Someone would say that a function should not be longer than 3 lines because now it is not doing just one thing. It usually does more than one thing. Well, my idea is the following. Try to keep every function focused on one important thing, okay? For this function, the important thing it is to understand and collect, well, put together all the prime factors without getting into details. So how exactly to add them to the result, or how to get the next prime number, because that is a separate task by its own, okay? This is the logic. It's not about the length of the code, or it's not about just having one if, nothing more, because now we have a double while loop, right? Nested while loops, but we are okay. So what we have is a solution, okay? It is a solution. It solves the problem and everyone is happy. Hope everything is fine on your side. Now, after doing this and after getting a 50 line of code, I want to switch to another approach to the same problem. For that, we are going to do some test-driven development, and I will try to show you how we could come to the solution, which will be absolutely different, to a solution of this problem, which would be much simpler and very straightforward. And I hope you will enjoy it. So for that, just forget about what we have. We are going to create a new environment, factors test CPP, and in the make file, we have a separated target for that. It is called test TDD. Okay, so I will do make test TDD. Just let's make sure what it actually performs. So it is depending on factors test CPP and factors TDD. We have never used them, and of course the HPP file is going to be with us. It is the same prototype, but we didn't touch these two. They are actually empty. So this is the test. It just contains an empty test, which makes sure that the testing environment is ready. And if I run test TDD, oh, I'm sorry, that was not the correct name. So factorizer test TDD, we will see that all these green indicators mean that something was executed well, it passed. Okay, now we have execution of this empty test and it was okay. Green means everything is fine. So we are going to do test-driven development demo. It is something very strange. I have learned it from Bob Martin, Uncle Bob, who is kind of one of the popularizers. I'm not sure if he's one of the creators, but maybe of this test-driven development methodology. And it is something quite different. I mean, given that we have experienced C++ developers here, you probably usually do the following, right? You have some non-clear set of requirements, then you create some solution, some code, then you sometimes test it, just write a couple of tests to make sure that some happy paths are covered properly. And you don't want even to get into those error cases because it's so many of them, or you didn't even cover them, so you don't want to get there. You have some working code, and then you show it to the user or to the QA team and try to get a validation. And usually you are going to have lots of bugs created. So now I want to show another way, another approach of doing coding. And it is called test-driven development. So in test-driven development, we are going to do test-driven development. We are going to do a very different thing. So here we have three modes. First one is called red mode. Red mode, it is when something is broken, so we create a test that shows that something is missing because we don't have any code. I mean, our code is now going to be this file. According to the make file, okay, this is what we link our code against. So test TDD, that is empty. We're not going to reuse the code that we already have, which is in, sorry, not test factors TDD. We're not going to have to use that factor CPP that we had. It would be cheating, right? So test-driven development tells us, first write a test that will fail. So a failing test. Well, we don't have any failing test now. Let's create one. Empty test. Okay, instead of empty test, I will check what about factors of 1. For factors of 1, I want to make sure that if I call get factors and pass 1, it will return, well, it's not going to be a null pointer, I guess. I guess it will be an empty. So I'm thinking about the requirements. I'm thinking like, what should that function do if I give it a number that has no prime factors? Of course, there are numbers like that. 1 is one of them. So I would probably expect an empty array or something like that, whatever it means, right? But we know that emptiness in our system, it means filled with zeros, okay? 0 means there is nothing here, don't look. So we can say, what if there is an array where we have a 0 at the first position, right? Something like that. So I would call the expect equals, which is a macro provided by Google Test Framework. I will give the result of these get factors and the 0, an array filled with zeros, and expect that they should be equal. But now we have, well, now we are in the red mode. Red means there must be something rendered on the screen, and there is. I have these huge and scary error which is due to the macros that they, because there's a define here, as you can see, this is a macro. Expect EQ is a macro which is expecting something from me, but I actually didn't provide whatever it is expecting. For example, maybe if I put this into some beautiful parentheses, it will, well, it's not. So what is the problem? Actually, the problem is that get factors is unknown, okay? But you will not get a very precise message about that. Oh yeah, we will. I'm sorry, in this case we will, but as you can see, the red line is not even under get factors. Okay, but the problem is with get factors. So it's a little bit confusing, but you will get used to that. Okay, Google test is a little bit confusing because of these macros that it is using. Well, okay, get factors, of course it is unknown. We didn't include the file, right? Now we include it. And I hope we are going to see another error now. And yes, it is. So it is about where exactly did I miss it? But it's not about our code, okay? It's about something that is outside of our control. It is somewhere in the macro, because here we don't, we shouldn't even have any commas or something. Okay, anyway, let's do it properly. I will put this casting. So this is the solution. I know this is not a correct way of doing things, but this is what we have. Okay, while using Google test, we need to do a little bit of kind of tricks. So this is the solution. Again, this is just a toy case. We need to go through it to understand the big picture. Now we don't have the red screen, the red things on the screen. So let's compile and see if everything is smooth. Well, it is not. Now we have something red, right? So error message is red, and this status is also red. So yeah, we are still in the red phase, which means now the linker is complaining. Well, of course, the linker would complain because the function, well, there's no function. It is just empty. It is missing. So I will create get vectors. No need for the header file because we just reuse it. And here we are going to put some implementation, okay? Just a placeholder so far. We will overcome the linker error. Just don't be in a rush. So again, we don't have anything red right now. If I do make, I get the executable file. I need to run it. I run it, and now I have something red. So we are still in the red phase. Now it is failing. Why is it failing? Because it says, well, we have null, but we were expecting this. Oh, were we? I mean, I wasn't really expecting this. What is this even? Obviously, the test is not properly checking for what we need, right? So, well, this function is just returning a pointer, and expect EQ would compare pointers, which is not correct. I mean, we need to compare the contents, right? So, okay, contents. Well, can we do it like this? What if I create a function? Let's call it bool arrays equal, or something like this. Arrays equal. We are going to provide two arrays, A and B, zero terminated, okay? Compares zero terminated arrays, because we know that both must be zero terminated, so we're not going to have the length here. Okay, a for loop which goes forever, because again, we don't know when should we start, because this is our break condition, right? So whenever we see that they are different, we return false immediately. But if we continue for some while and we get to a zero value, so AI is zero, but it is different from BI, so we should stop, obviously. And equal, well, if they were different, we would return false. So if AI is zero and they are equal, well, both ended, right? So this is the logic, a very strange logic. Zero terminated strings and arrays are really strange. So now I'm going to call arrays equal instead of, well, comparing two using the macro, but the new macro is expect true. So expect true, make sure that whatever we give it is true. And whatever we give, that is the comparison of arrays. Okay, this is just a setup. It takes a little bit long, but yes, don't hurry. We need to make everything right. So I run it. Oh, segmentation fault. So it's not properly read, but here is the red thing, okay? We still have something red on the screen. The failing execution of the test. Whatever fails, in this case, the system fails with segmentation fault, but still we can see it, right? That this is the failure. Okay, what is wrong? This is wrong. We didn't actually do a good job. So for that, I'm going to do a little bit kind of cheating thing. I'm going to copy this part because it's not properly related. We know the correct way, right? We should create a class and handle everything, encapsulation, but it is out of scope. That's why we don't do it. Instead of that, this is what I do. Instead of null pointer, I will just return the result. Okay. Null pointer is bad, okay? Ta-dam, pass. So, yeah, we did a couple of hand tricks and got it passed. Looks like we didn't actually implement anything. Yes, we didn't, because there are actually no factors of 1, so why bother? Okay, let's move on. Oh, yeah, by the way, I'm sorry. We are now in another phase. The situation changed dramatically because now we don't have anything red on the screen. No one to complain, nothing to complain about. Now we are in green mode. Green mode means we have implemented just enough code. Well, we can say that red mode is when we write the test, and green mode is when we make the test pass, implementing just enough code to make the test pass. Okay, we can use that terminology. But at the end of the green mode, we should see only green things. Now we are there. And there is one more step. I will get to that a little bit later. So we can just go back to the red mode, which is create a test that will fail. Okay, what about vectors of 2? Well, vectors of 2 would contain 2, but it would look like this, right? 2 and then a 0, which means end of array. 1, 2, and then end of array. Okay, I have the test. Does it pass? Well, no compile time errors. If I run it, it fails. That's great. Okay, that is a good feeling when you create a new test and it fails. It means you are on the correct track. I mean, if you create a test that doesn't fail, then what was the purpose of that test? Okay, a failing test means you have identified a new weak point. Okay, let's go and fix it. What is missing? Well, we don't really have anything for that. We are not ready. What if I add 2? Because I know that 2 is the factor which will help me to go through this test. Well, let's see. I'm kind of guessing. But no, everything failed. You see what happened? So both tests failed, even the one. Why did it happen? Well, because for 1, we should have no factors, but we add 2. So, okay, I'm going to add an if and say, if that number is greater than 1, then add factor of 2. Okay, looks like a silly step, but let's try. And it works. Now we have both tests passing. Soon we will see that something more is missing, but let me do something for you. So initially, we had an empty result. Then I did something. So instead of empty, I started returning 2, but I also added an if statement, right? I'm just tracking what happened, what kind of modifications I did, because this code is going to evolve a little bit. Now, this is not a placeholder. Okay, we are in kind of okay phase. Everything is fine, which is bad because we are doing TDD. We must break it, break everything. Okay, let's break it. What if I take factors of 3? I hope my code will fail, right? Because I didn't do anything for this value, like I'm not ready for it. I'm hoping that I will get into that, yeah, failing test. Great. And pay attention that only one test is failing, okay? Only one. All the others are okay. Yeah, no problem. So we have 2 and 3. If I add one more if and do a little bit of more complicated things, it will make my code look really ugly. I don't want to make it really ugly from just the beginning. Instead of that, what if I just return the number instead of 2? You see? For 2, it was 2. For 3, it would be 3. Let's just return number. Let's see. It fails. Why does it fail? Okay, let me see what is wrong here. Now, we don't really see the internals, but we can add a little bit of debugging information right here. So whenever we see that some values are not equal, I can output. Okay, this is a little bit of cheating, because the proper way would be to provide 2 arrays to expect equal, and it would show me what is really different. But as we are in this zero terminated array situation, we need to kind of go through it. Okay, I'm just going to print what values are actually different. Okay, so AI is different than BI. This is what we print, and I need to include something. Include IOStream. So let's see what exactly makes difference, because our code is not really good at the moment. So let's go and see. Here it says 2 and 3. Why would be there a value of 2? Like, how come that we have 2 in our array? The result. Well, the problem is that we have a global array. That's why I told you not to have it from the beginning, right? So we have it, and here are the consequences. How to resolve them? Well, make sure that the array is clear after every test. So this is another very well-known thing, okay? Make sure that the environment is clean before or after every test execution, okay? Before every execution, because otherwise, interested in. So, and it will just do the following: put 0 into the index, and put 0 into result 0. So it means a 0 terminated array, right? We don't care about the other values because we have 0 here. So, and we need to reset the result just before every factorization. This is the problem, why we have 2 and 3. We are expecting for 3, but we have 2. Why? Because we have both of them. Save it. Oh, yeah, I didn't compile. So make, run. Great. All the tests pass. Now you can think for a moment that looks like I'm doing some silly things. I'm kind of just making some silly collection of tests to pass, writing some silly code. But yes, this is what we do. Now let's just track the transformation. What I did, I took 2, right? So there was a 2, and I transformed it into something which depends on number. Now it is a variable, okay? I generalized. Instead of a constant, now I have a variable. That is a great step. Just remember it. So now we are still in that green phase, nothing failing. So let's create a failing test. Okay, and for 2, 1. Okay, so we have a capacity of 100. So okay, we still can do that. We have 100. That is our limitation. But till that, we are okay. Let's make all good, run, fail. Only this test. And what is wrong? Well, 4 and 2 are not equal. So 4 and 2, I was hoping to have 2, but I have 4. Why is it like that? Because, well, what I have, it just adds 4, right? If the number is greater than 1, it just adds the number to the factor list. But 4 is not really a correct number to be added. So I'm going to do this. I will add a little bit of check. Well, if that number can be divided by 2, then I will add 2 to the factors. I will divide number by 2, and then I will add that number. It looks like it will solve my problem. So actually what I did, I added one more if, right? I added an if, but I'm not sure if I did everything properly. So I still need to check. Yeah, let's go and check. Oh, but now factors of 2 is failing. Why is like that? Because after, you see, imagine now we're checking for 2. It can be divided by 2. Okay, I add 2. I divide it by 2, but then I add again. But what I add is 1. Let's see. So 1 instead of 0. I have an additional 1. 1 is not a prime factor, so I should not add it. Okay, one more if. If number is greater than 1, then add it. Okay, so only factors that are greater than 1 should be added because, well, 1 is not a prime number. That was wrong. And pay attention, our test actually catches the situation. That's great. Now all the tests pass. It's a set point because we need to go and think about another test. What about 5? Is our system even ready for 5? We didn't make any checks, anything. Most probably it will fail, right? Because it must be very usual to fail. So factors of 5 is just 5. It is a prime number. Make, run, and it passes, which means, well, we didn't add any value. So why does it pass? Yeah, let's go and check. So here we have number is even case. No, it's not even, but it is greater than 1, so it will be just added. Yeah, so, like by mistake or by some chance. Okay, we didn't actually cover it properly, but it is covered. So we just move forward. We no time for sitting and getting sad for a passing test. Of course, it's a sad situation, but we are in the middle of the process, right? So 6. Well, it can be factorized to 2 and 3. Most probably it will fail, right? So why would it even pass? But it passes because our code is kind of more or less covering a couple of simple cases, and 6 is just one of them. Obviously, we divide it by 2, get 2 as a factor, and then whatever we have, it is 3. We add it because it is greater than 1, right? Yeah, it looks like I'm doing silly things. Just be with me. We are almost there. What about 7? 7. Well, it shouldn't be covered, right? We have never done anything particular, but it does because 7 is just another prime number. Same case as for 5, like exact same case. You can check that the code is just exactly the same workflow. Okay, what about 8? I hope that we are not ready for 8. I mean, that would be really strange. 8 has 3 factors. Okay, obviously, we are not ready for anything like that. And yes, it is failing, and that is the only failing test. Everything is great. Now we are doing good job. So 8, well, 8 is a number which can be formed by 3 multiplications of 2 by itself, right? So if we add 2 and then divide by 2, we still have 4. And by the way, if we go to the output, we will see that we have 4. Yeah, why 4? We should divide it by 2 again before adding, right? So I am doing now a magic trick. Follow my fingers. So while instead of if. While is a generalization of if. We have already seen it, right, today. So I transformed if to while. I'm keeping track of what we did. Make, and all pass. Why? Because here we just keep dividing the number by 2 so long as we can. 8 is a very good case for that. It really gets decomposed, factorized. Okay, we are now again on the same sad situation, okay, when all the tests pass, and then I challenge my system with 9. I'm almost sure 9 will never be covered. We never cared a bit about 3. We were focusing on 2 so far. Yes, and it is failing. Great. With what? Well, 9. Well, looks like 9 is in the list of our factors, which is obviously wrong. But let's check. So here we have a block of code which is about 2. That's why we covered 8 that easily. What if I just copy this and make it also for 3? I mean, if it can be divided by 3, then just add 3 as a factor and divide it by 3. Looks like a very silly solution, but what if it's right and it works? I believe it will. And yes, it will, because, well, same situation, right? 4 and 8 were covered with this, and 9 is just covered with this. Yeah, but I just copied code, okay? It's evil. So never copy any block of code, because after you copy a block, usually you need to take care of many things, taking care of values, okay? Don't do that, and it is a bad practice. I mean, usually that is the main reason why the code starts behaving wrong when the system gets larger, because you have copies of pieces of code. So just eliminate all the copies. What can we do here? I'm just going to eliminate this. Never do like that. But we have passing tests, right? So I'm going to introduce a new mode, which is the refactor mode. And refactor mode is when I do a code cleanup, because I see I did an ugly thing. I duplicated the code. That is really bad. So I'm going to declare a variable. Let's call it factor. It will be 2 initially. And I will try to divide by factor. And if it gets divided, then I add factor and then divide the number by factor. Looks like I covered the case for 2. But then I also need to cover other cases, right? I will do like this: factor plus plus. Just move to the next one. But we need to get back. So in order to get back and make sure that we cover 3, I need to put this outside if and make this if a while, because I will never get to the next iteration, right? And this part is not related, so I will put it after. Let's have a look. After a couple of transformations, what I did, it is the following. I transformed 2 to factor, so another constant to variable transformation, and another if to while transformation. Okay, now I have this while, that while, hopefully. Yeah, now I can be sure that I didn't break anything just running the tests. That is a very strange feeling when you can be sure that you didn't break. Usually programmers don't, when all fail, yeah, for sure, we did something wrong. But in case of TDD, whenever all the tests pass, we can be sure that everything is fine. Because we covered every case, because all the code was driven by the tests. We don't have any additional code. We were compacting, reducing the code. How could we get even more? We never get more code. So all the tests pass. We are all good. Just move forward. What would be the next step? Well, we have covered so many special cases, 1, 2, 3, every number. What if I put 10 and then 11 and then 12? Well, another rule says As the code, as the tests get more specific, the code gets more generic. This is the rule, okay? We just show it. I just show it. I had two ifs checking or covering, sorry, not ifs, whiles, covering for the case for 2, for the case for 3. It would go till infinity. That's why I compacted them and generalized them. That's how we get to the solution. We generalize the code, but the tests get more and more specific. They cover more and more cases. Okay, now shall we try 10? Yeah, let's try. Factors of 10 would be 2 and 5. Is our system ready for that? Well, it is. Now I'm kind of stuck. Should I continue with 11? 11 is just another prime number. It is covered. 12, it is kind of boring. What if we go for kind of all-in? I'm going to do an all-in and do a factors of n, where n is going to be a large number. So that number is going to be formed as a product of a bunch of this kind of bunch of prime numbers. Just make sure that they are all prime, okay? Because our system is just for primes. And what I expect from this number when I factorize, I actually literally expect its exact factors, because these are the factors. Because prime factorization has only one form. It is unique. It cannot get two different prime factorizations of the same number. So it is 2, 2, 3, 5, then 7, then 11, and then at the end we put 0 because it is 0 terminated. Right? Most probably it will fail, right? Because we didn't do anything for that. But it doesn't. And that is a point when the change in thinking happens. So right now I'm sitting in front of a code. Here it is, some code which I just wrote, but I have no idea what is written there, and all the tests pass, and I don't even know what else to check. But okay, I know something I can check. I can do one more test. I can take a huge prime number. Do you know any large prime number? An example of factors of large prime. Okay, let's take some large prime number, and it will be some, I don't know, really large prime. Like 73 is a prime number, right? Well, it's not really big, but it is a prime number. So I'm hoping that my system is ready. I've never done anything for that, but it is ready. You can find another large prime number like 5 digits, 10 digits long, whatever. If it fits into integer, okay, 10 digits is too long. 5, 6 digits long, and you can try. So what we have now is a strange feeling, because I have some code, but by the way, the code contains a duplicate part. This part looks a little bit duplicated because I had the same condition checked twice. Now I stare at it for some time and decide, what if I just remove it? Like, is it even adding anything to my code? Does it make any change? Well, actually it doesn't, because the whole number is already divided and it's equal to 1 actually, so that condition never meets. So now I have an algorithm, but I have no idea where it came from. I never sat down and created this. And if you ask me, I'm not even algorithm, you will not, but it is. Why am I sure? Because I have covered all the possible degenerate cases that are so unlikely to happen. All the far from center, okay, all the peripheral cases. And then I got to the center step by step, and at some point, turned out that I'm there. I mean, first time when I saw this demonstration by Uncle Bob, I wasn't even aware that we got the solution. I mean, he executes it and said, like, what? How did we cover that case? Why is this algorithm actually covering that case? Well, because just go through it. What we do here, while number is greater than 1, well, try to factorize. We start at 2. We divide by 2 if it can be divided. Then we try for 3. Then we try for next number. Okay, it's not even about prime numbers. But when we start at small numbers, we never get to 4. I mean, if it could be divided by 2, we have divided by 2 twice. So it will not be divided by 4 again. Okay? I mean, yeah, maybe we can prove that this is also another algorithm that covers the same situation. But if we start from this, it will be hard to convince even me. But now I have all these tests and they give me the confidence. They show me that my system is perfect. Are you still here with me? So let's try. Again, this is a very strange situation for programmers. Usually you don't have that feeling that, oh, when my tests pass, I can just ship the code. It's never like that when you are in a company dealing with production code, because you never do TDD. That's the problem. Programmers usually don't do TDD because it's very hard. Usually problems are so big. Where to start with? But that is the problem of the modern software. The problems are big and we just start somehow and we somehow get through it and somehow get some code and try to make it fit the expectations and deliver it, and then we get tons of bugs. But if we figure out small pieces, decompose, okay, the big problem into smaller problems, and each small problem developed doing TDD, we will get clean solutions. And then if we put all them together, it will be a perfect solution to the given problem, and you can deliver it and you will not get problems anymore. But it is so hard because of the mindset, not technically, but the mindset is the problem. And all these transformations we did, they matter, and they are called literally transformations in TDD, and they have priorities. And whenever you follow the prioritized list of transformations and apply them to the code, whenever you get to another failing test, you will be on the safe side and you will get a really good algorithm. But also one more principle here. Start at the most degenerate cases and get to the center gradually, okay? So step by step, without hurrying, without jumping into the main algorithm. Never do that. Never sit down and create the whole algorithm. Okay, we didn't do that and it helped us. Okay, now let's try the following. Now we have another implementation. What if I plug this implementation into the main function? Is it even legal? Like, will they work together? Let's see. So what if I take my main CPP and the factors TDD? Yeah, I have created makefile earlier, okay? Yeah, just to save time. So what if I run, so I will run make, it is called main TDD. Now I'm just putting together main CPP and factors TDD. This is factors TDD, this is this. But the idea is I have the same interface, right? Yeah, the implementation is completely different, but the interface is the same and it should work. Well, let's see. Oh, let's see how it works. I will run it. It is called factorizer TDD, I believe, right? Now it is asking, it is the same main code. Now it is asking for a number. Okay, what about 10? Oh, got properly factorized. What about 1024? Oh, looks like it is okay. What about 73? Still okay. And we can do the opposite also. We can try to test. Now we have a collection of tests, right? They are very independent from the implementation. And what if we plug it to the old implementation that we used to have, get vectors. So I don't really foresee anything, but if it fails for whatever reason, I will not be really surprised. I mean, because I didn't actually test everything. We didn't do any test-driven whatever here. We were just writing the code, hoping for the best, right? So for the opposite, we have one more, where is it? Another case. So we are going to put together the test and the vector CPP. Okay, it is called test. It is not created with TDD. This is our code, the old code. So I'm going to do a make test. Yeah, it gets properly linked because the interface is the same. We didn't break anything. The interface is correct. But the output is called, where is it? Factorizer test. Okay, so I'm going to run factorizer test. And now we get a bunch of tests failing for whatever reason. Did we try all of these cases? Because we didn't, right? I ran the main function, well, a couple of times. I entered a couple of numbers, maybe 10, maybe, oh, did I check 10? Maybe I checked 8, a couple of tests, right? So here we have lots of errors, and it can be because the test doesn't actually fit the code. But as we can see here, yes, I know, I'm sorry. So there is one more thing we didn't properly cover. The thing is that reset results is called only in these get vectors. So at least we know that this code contains an error. And that error is that every time dealing with the global variable, we don't clean the state, okay? Cleaning the state is really crucial, because otherwise two executions are going to depend on each other and are going to make problems. So I will just bring it here. And if I try again, hopefully now we'll get some of, all the tests. Now, yeah, great. So it turns out that we have also created, we have done a great job, and we have actually covered all the cases, and also this implementation is ready. Like, yeah, we have covered everything. They are kind of equivalent. But if you look at it, I mean, imagine you are the code reviewer and you have a code of 60 lines. And on the other end, you have a code of, well, all the comments together, it is just 40 lines, and there is just actually 2 functions that really are doing something. Reset, it's very clear. I hope this kind of code will make you happier than a code like this. And on the other hand, TDD gives a new way of thinking, a new type of a new approach to programming, which is really strange. I mean, for programmers, that feeling of being sure that your system is correct, that is a strange feeling. Usually we don't have it. So it is good for a new project. When you start a new project, you can split it into smaller pieces. Each piece can be done with TDD, and then you combine them and you are happy. But if you have an existing system, it's hard, because now the code is there, you are late, you cannot do a TDD anymore. But what you can do, you need the requirements. You need to create a test set for the existing code, then remove the code and try to rewrite it. So if you have the test, I mean, if you create a test, then remove the code, you will be kind of in a test first situation, and you can just write it in a way that has node applications, has a cleaner architecture, has, well, satisfied the solid principles, etc., and can be a better code. So testing first approach gives better results, but usually programmers don't do that because of a couple of reasons. First, programmers are lazy, and second, you usually don't have all the requirements. It's hard to create tests first when you don't have requirements. We know what it means, right, to factorize a number. We know the requirements. That's why we could do this easily. But when you are dealing with a a complex system and you don't have all the requirements, it's hard. But the good side is that you are not going to create some code which will be wrong because of missing requirements. You will clarify the requirements first, and then you will create code that matches the real requirements. Okay, this is all from my side. This code, so this session will be shared on YouTube, and the code will be also available in the description if anyone needs to access it. I hope you enjoyed it, and if you have any questions, I am open for some discussion or Q&A session. Just let me know. Any questions? Yeah, sure, you can write. I'm reading. Hope you are writing now because I don't have anything. Okay, regarding cleaning the results, this is TDD logic inside business logic. It is not ideal. Cleaning the results. Cleaning, you mean resetting? If you are about reset, then that was just, well, I had to do that because the global state, which is a wrong solution, needs to be properly cleaned after every use. So if you have a class and that array is inside your class, then you need somehow to reset it every time, right? Anyway, you need to reset it. But or you need to copy the result. So you create a result and then copy and return to the user. In that case, you don't need to reset it, of course. But in our situation, because of the global state, we need to reset it every time. Okay, thanks for the awesome session. That this stuff was absolutely magical. Yeah, great. Thank you. Do you think it can be used in with finite state machines? Well, actually, every program is a finite state machine. If you think about it, every program, it has some state and you check something. So you get some input, and based on the state, you perform some actions, which usually change the state and produce some output. Actually, every program is a finite state machine. And I really don't know what exactly you mean, but my answer is yes. I mean, yes, you can do TDD because you can do TDD with any software. I thought it was code that is specifically. Oh, no. The reset code is just a regular logic because you need to make sure that any test doesn't affect any other tests. That's why we need to clean. Even there is a better solution. Test environments have some tier down functions like gtest has. You need to put that cleanup code into that block, and it will be called after every test. Okay, that would be a more precise solution. Okay, one more question. How do I know when my tests are good enough and covering all important test cases? My guess is we can never truly know. So the idea is to start as far from the central implementation as possible. I mean, you start with very unlikely degenerate situations. You check the null cases, you check impossible cases, and then you gradually get to the main state. And when you get it, you are done. All your tests are there because you have already covered all the degenerate cases. Usually we think in the opposite way. First, we do the happy path, okay, the positive case. Then we start thinking, oh, what did I miss? But when you start from the other end, you will never miss them. I mean, they will be the first. They will come the first. And as long as you transform the code, refactor the code according to the laws that I presented, you are going to have like clean code, and you are going to have some confidence, good level of confidence in your tests, because all your code is driven by your test suite, and your tests are driven from the requirements, driven by the requirements. And you started with the most degenerate cases, and you gradually came to the central solution. That's why they are all good. I mean, It's a very strange feeling, I know, but just check. I mean, you can try yourself. Try to solve some problem using TDD and like challenge yourself to to find a bug in it. Okay, that's right. All programs are state machines. I was mainly talking about some switch statement that was switching over some enums and mutating some booleans and stuff. So I guess the answer is just yes. Well, basically the answer is yes, but I would not recommend to have a code like that. I mean, from the object-oriented design perspective, a code like that is usually a lack of proper design. Okay, that's why I would suggest to do TDD and follow these rules. By the way, if you just Google, you will find the complete list of transformations ordered by priority, and always try to apply the higher priority transformation. You will never end up with a switch statement. That is one of the lowest priority things. You will find another solution to that. Okay, but yes, if you end up with something like that, but you have the TDD tests, so they cover it anyway. Okay, thanks for the questions. Looks like we're out of questions. Thanks for coming, for joining. That was the first one. I'm not sure how helpful it was. I will be happy if you can share your thoughts on social media about this session to give it more visibility, because it is just for the community, and yeah, I'm just trying to make it as visible as possible. Thank you very much, and see you next time. You will get the next event on your calendar if you are registered. So see you next time, and take care. Try to apply these practical advices in your daily life.